In this video on regression, we're going to look at some of the issues with trying to get the best regression model. So, starting out here, we have the model we had last time. So here we've got our data from last time. We're looking at the states data still. So looking at the states .mtw, and we're looking at the verbal as the response percentage predictor. We're fitting the linear model, like the simple linear model, and we got this equation, right? We got the SD verbal is 485.4 minus 1.105 times percent. So that's our linear model, which is y equals a plus bx. So y here is the average verbal score for the state. X is percent. A intercept is this 485.4, which makes no sense by itself because 0% taking the test makes no sense, right? If 0 take it, there is no average score. But the slope makes sense. The slope tells us on average if percent moves by 1 or by ever how many, then the verbal moves on average down by 1.105 times that amount. So if percent on average increased by 10%, verbal on average would go down by about 11 points, 11.05 points, 10 times that, negative 1.105. So we looked at that last time. We also looked at last time that the distances between the points and the line, right, those are our residuals. And R squared kind of comes from the residuals and how far the points are from their average, the mean of the y's, right? So these lines here, these are called residuals, leftover distances. That's the unexplained stuff. So those are residuals. Okay, so what we're going to do today is, first thing we're going to do is we're going to try and fit other models rather than straight lines to this data. So as it says up here, at the beginning here, we can see there's actually a curve in the scatter plot. You can kind of see from the red point, it's more of a curve. So maybe a line, a straight line, not the best model to fit. Perhaps better to fit a curve. So we're going to try to fit a quadratic and a cubic model. Okay, so if we scroll down, that's what we have down here. I guess before we scroll down, I'll show you how to get those from Minitab. Same place you got the linear model. So if we go back to Minitab and get Minitab up here, remember to get these graphs, we did the stats, regression, fitted line plot. So I want verbal as my response, and I want percent as my x, my predictor. I fitted the straight line before, that gave us a straight line, but I can fit a quadratic. And there it is. There's the graph of the quadratic, which we'll see in a moment on a handout, but that's the same as what we have in a handout. Or I could fit a cubic. I notice it's a quadratic, I guess. Notice it's a quadratic because here I've got percent squared, right? That makes it quadratic. It's got a squared term in there, the x squared, percent squared. If I now do it with the cubic rather than quadratic, notice now it has a percent cubed term in there. So it's a cubic. Okay, so those are the graphs we have down here. If I scroll down, I have those two graphs here. And I think it gets, let's see, we're about right there. I can get most of it in, right? Actually, let's see if I move it down a little bit. There we go. Okay, so there are our models. Okay, so this is the quadratic, right? This is the quadratic right here, because it's the form y equals a plus bx plus c x squared. Right, so you've got your a term here is 506.5. Your b here, your slope, is negative 3.145, and your C the constant for the squared term is positive 0.02797. And r squared, we can kind of see up here, r squared is 84.4% or 0.844. So in this case, it's hard to interpret the slope by itself because the model's changing. It's not linear, right? So we can't really say that this is change in y but change in x because also the c also changes x. So it's harder to interpret the model. Down here we have the cubic, right? This one here is the cubic because we have a percent cubed term. So it's the form y. So this is the quadratic. Up here, the cubic. We now have so it's a cubic model because we now have a cube term in there. So here again we could go through and see what each of the values are. So here's our A value, the 506.4. B is similar to what was before, negative 3.129. C is similar to what it was with the quadratic. It's 0.02747. Now we have this very small d term, right? D here, this d term is points. Let's see, 1, 2, 3, 4, 5. My eyes are good. It's like 5 zeros and a 4. Okay. And notice r squared here is still looks like 0.844. Well, what was r squared for our linear model? Well, if we go back to the linear model up here, so if the linear model, r squared was 0.744, right? 74.4%. Remember 74.4% of the variation in x is explained, and y is explained by the model. So notice r squared jumped up quite a bit from the linear, the 0.744, to the quadratic 0.844. What it's telling us is that these points are closer to this curve. The residuals are smaller. Remember we were looking at the sum of the residuals squared? So that really the sum of the residuals squared is smaller, but in general you think about the residuals being smaller on average. These residuals are smaller. So the points are closer to the model on average. Which implies a bigger or higher r squared value. And that's what we see over here. R squared's gone up. For the linear model up the top here, the points in general on average are further away. At least the sum of the square of them were. Now on average they're closer for this curve. And that makes sense visually. Visually we can see that. Visually we can see the points. If I get the straight line up here, get it in here too, we can see for the straight line the points, some points are very far away, while for the curve they're all pretty close. Remember, that's how we calculate r squared. R squared is looking at the sum of the residuals squared, and the smaller that is, the bigger r squared is. But when we get to the cubic model, let's scroll down and get the squared and cubic here. Ooh, a little too far. There we go. For the cubic model, if you look at it, it looks the same as the quadratic model, right? Visually, you can't see much difference. That's because the cubic term is very, very small. This term here is very small, right? It's 0.00000004. Or visually, maybe I'll use a different color here, getting too much blue on here. So if a cubic model is useful or good, what should we see? Well, remember, what a square and cubic does. A square term, a quadratic term, which we see up here with the quadratic, allows us one curve. That's what quadratic does, right? X squared, it allows you one curve. A cubic allows you two curves. Do we see two curves here? No, it's just like one curve. So if a cubic model is useful, you expect to see two curves. Here we don't. We just see the one curve. Likewise, if x to the fourth was a useful term, we expect to see three curves in the model. So visually, it seems like we're not getting much extra by adding the quadratic term. It's very, very small. The d term here is very, very small, 0.000000004. So it's very small. Notice r squared hasn't changed much too, right? It looks like the same r squared. Actually, it's not. This r squared for the cubic term, this 0.844 for the cubic term, is actually slightly larger. Because what it's doing is if you keep adding x terms to the model, so I guess we'll scroll down here a bit and write some stuff down here. Now it says which model is best, linear, quadratic, cubic. Well, one thing which, if you think about it, makes sense is if you keep adding x terms to the model, predictors or independent variables, so to the regression equation or model. So if you keep x terms to the regression equation, r squared has to increase. Because if the new x term isn't useful, it'll just be 0. And so I guess we'll say unless the constant or coefficient for the new x term. Let me erase that one. That term's not very good. The new x term is 0. So here, if we go back up here to the quadratic and cubic, if this value d was 0, then it's what would happen is the a, b, and c be exactly the same as you have for the quadratic model. It'd be the a would be this 506.5, b would be the negative 3.14, and 5, and so on. Or the model wouldn't change. R squared would be exactly the same. But as long as when you add a term, that term isn't 0, here it's very close, but it's not quite 0, right? It's 0.000004. The points get slightly closer to the curve. If they don't, that term would be 0. So r squared has increased. This r squared 0.844, if you go up more decimal places, is actually slightly larger than the one we had with the quadratic, the 0.844 there. So hopefully that makes sense. If you keep adding terms to the model, r squared has to increase. As long as those terms aren't 0, it's going to increase, because that's how r squared works. It makes the residual smaller, makes r squared bigger. So here, knowing that, if we look at our models, which one is the best? Well, it seems like the quadratic is probably the best. The reason is, if you look here, so say for this data, probably the quadratic model here, so the quadratic model for this data is the best, because visually a curve is a better fit. Better fit. So better fit. I did it again. Oh, must be one of those mornings. Let's see if I can write fit this time. Better fit to the data than a straight line. And a cubic doesn't add an extra curve. Or r squared only increases very slightly, because that d term is very small. Okay, so for our data, the quadratic seems to be the best. Cubic doesn't seem to add anything extra. Obviously, it's better than a linear. R squared increases a lot, and visually it looks a lot better. The curve fits data a lot better than the straight line does. So that's sort of just visually kind of how to kind of figure out what model might be best. But of course, there's more to it than that. Oh, a little too high there. Let's go down here. There we go. Other issues. You can have more than one X predictor in your model. So for example, say we're looking at why our response is maybe someone's student's college GPA. Well, what things might affect that? Well, one thing could be the high school GPA. Another thing could be their sex, male or female. That might affect the college GPA. Males are a little more bimodal. Some seem to party too much and to study, while women are more sort of a little more uniform as far as their habits seem to go, as far as grades seem to go at least. Other things could be maybe we could have a third variable, could be parents you do individually or parents' combined education background. So in other words, maybe you look at the total number of years in school for both parents combined. Or you do each individual parent separately. Maybe parents' combined income. Maybe that has an effect too. Who knows? But there are lots of variables you could look at. So you have more than one predictor. So I could have y equals, for example, a plus b x1 plus c x2 plus d x3 plus e x4, and so on. So since there are lots of predictors, you got a question here: which of these x's are really useful? In predicting y, because that's one thing you do with a regression model, right? A regression model is you're looking at a relationship between y and one or more x variables. But a lot of the time you want to use the model to predict future values. Okay, I've got this model now. I think college GPA is related this way to high school GPA, this way to sex, and so on. Now if I have someone apply to college who has this high school GPA, who's female, whose parents have this background, how do I think they'll do in college in general? How I think what will their college GPA probably be? So colleges may use that type of thing to kind of decide who are better risks, I guess, if you think of it that way, or who are more likely to be the good students and who are going to maybe struggle a little more. Of course, it depends on individual, but that does give some information. So one thing you use regression models for is try and predict future y values. So it's used for predicting. Another thing is you can create almost any model you want. So let's say we've got the same example we have above here. So same data down here. But I don't have to just have linear terms. I could have like y equals a plus maybe b. Maybe I'm going to take x1 times x2. Interaction. That's called an interaction term. Interaction terms, for example, in biology and chemistry, oftentimes make sense. Right? One chemical by itself isn't very reactive, but if you combine two of them, it becomes very reactive. So interaction terms may make sense. Other things you can do are, like maybe I'll take, I don't know if it makes sense here, but we'll take x4 divided by x1. That's called a ratio term. Ratio term makes sense. For example, in baseball, you might have, if you're looking at number of hits, that by itself tells you something, but if you take that divided by at-bats, that makes more sense. How many hits they have per at-bat, that's a ratio term. So those sometimes make sense. But you can create all funky type terms. For example, you could have like, obviously x to any power, a power term. You could have x3 to the 4th power. It's a power term. Not quite sure here why a 4th term, but squared, it seems like a squared might make sense, right? If you've got a curve in the data. Not sure why you can justify maybe a 4th power. Another thing, I guess I'll do it here. You could use, for example, natural logs, right? Natural log of x1. Or you might have e to a power. So logs and exponentials. Those might make sense because of, again, in the physical sciences, for example, in biology. Let's just say bio there. For example, you might have exponential growth and decay. And that also happens in finance, right, with money. You can also get the exponential growth and decay. Plus, you could have other things. You could have h cosine of x and x3 or whatever and so on. ... You can create almost any terms you want. So the question here is, well, the thing here is, I guess we'll say, how do you find the best model out of all these choices? Overriding principle here is going to be KISS when we do this. Hope you know what KISS means. KISS means keep it simple. And since we're doing statistics, we'll say statistician. But it could be stupid too, right? So I'll say that. So keep it simple. So in other words, the regression model you create has to make sense to you. Let's get a better U there. Come on. Yeah, the regression model you create has to make sense to you. You need to be able to explain why each x term is useful, why it makes sense to have it in there. And that's the problem some people get into with regression. They get overly fancy. They say, ooh, let me try this, and this. And they say, hey, this fits it really well. But so you get this fancy model with logs and cosines and stuff, but what does it mean? How do you interpret it? And that's why you get into trouble. It has to be simple. That's why you have to keep it simple. It has to make sense. It has to be something you can explain why that model makes sense. So most of the time when you're doing regression in real life, you have to use data you have some background knowledge in. You have a background so you know that, well, does an interaction term make sense? Does a ratio term make sense? What kind of terms here do make sense and why? So that's why you want to try and keep it simple. So we'll go ahead and stop here for now, and we'll look at next time kind of how to do this stuff on a computer, because you're not going to do this stuff by hand. You're going to let a computer create a model for you, and then you're going to test the model and see which is the best model and why.